Hello everyone. In this session, I will be giving you an overview of the finite element methods. I will be providing two levels of explanation, the first in layman terms and the second involving some maths. But why study FEM at all? FEM has become an integral part of the design and development of numerous engineering systems. It is used in aerospace, automotive, electrical, electronics, power industry, construction, healthcare, and possibly many more. Do you know it is also used in the chocolate industry to make sure that the chocolate does not break during packaging? So, if you are going to be in the design and development, it is necessary to learn FEM. Let's take a step back and look at nature. We know that nature operates via gradients. For example, a gradient or a difference in pressure drives the wind. A gradient in temperature drives the heat, etc. Similarly, most engineering systems are represented by gradients and we commonly call them as the differential equations. Here are some examples from different fields. Cauchy's equation in solid mechanics, Navier-Stokes equation in fluid mechanics, Maxwell's equations in electromagnetics. In engineering problems, along with the differential equations, we also have additional constraints at the boundaries known as the boundary conditions. The differential equations together with the boundary conditions are called as the boundary value problem. Looking at these equations, even a grown man will weep. We don't have any other choice but to solve these boundary value problems in order to design efficient engineering systems. Lastly, this boundary value problem is defined for a specific domain or a geometry. If we look at the solutions to boundary value problems, the analytical methods are applicable only for simple geometries as shown here. This stuff you might have studied in your undergraduate or graduate maths courses. Now, the question is, how do we handle complex geometries which are common in real world applications? And the answer is using numerical methods. Okay, now what is FEM and how is it related to all these? You'll get your answers, don't worry. FEM is a numerical method which is used to obtain approximate solution for a given boundary value problem. This is what it does. It takes the boundary value problem and converts it into a linear system of equations of the form Ax equal to b. All those complicated equations you saw earlier will be converted into simpler forms. And as you know, Ax equal to b could be easily solved using a computer. This is really important and let me emphasize these 2 points again. Number 1, FEM is just a numerical method. Number 2, FEM converts a boundary value problem into linear system of equations. Keep this in mind. Let's look at the process of FEM or learn how FEM works. To illustrate, I am taking a rectangular plate as an example, but remember, this is applicable for any shape. Let me remind you that the objective here is to find the solution you had for the boundary value problem in this domain. In the first step, we divide our original geometry into smaller pieces. Each smaller piece is called the element and all the intersection and corner points are called as the nodes. The process of dividing itself is called as meshing and it is one of the key steps in FEM. After meshing, we consider one element at a time and perform calculations. Likewise, we do our calculations on all the elements separately. Next, we assemble all this information together and we obtain the solution you had at all the nodes of the domain. Lastly, we do further calculations to obtain the field solution for the entire domain. That's the whole picture of FEM in layman terms. Basically, it follows the divide and conquer process. However, the beauty of FEM lies in its mathematical treatment. Let me give you a flavor of it without getting into finer details so that you appreciate the FEM better. Let's consider the same geometry as before, but here we divide this into two regions. The outer boundary is called as gamma and the inner region is omega as shown. To show the mathematics, I am taking a boundary value problem with the Poisson's equation, which is dou square u by dou x square plus dou square u by dou y square equal to phi. Of course, there are also boundary conditions associated with it defined in gamma. If we consider ue as the exact solution, then it must satisfy the above equation. So, we will have dou square ue by dou x square plus dou square ue by dou y square minus phi equals 0. As I mentioned before, it will be very difficult to obtain an exact solution for real-world problem. Instead, let's try to find an approximate solution u hat. Since this is approximate, it will not exactly satisfy the Poisson equation. Hence, we'll have this term not equals to 0. And let's call this as the residual r. To get a reasonable u hat, we must try to make the value of r as close to 0 as possible at each point in omega. So, to make r close to 0, we define what is known as the weighted residual statement. Here, we integrate the product of the residual with a known weight function w over the entire domain and set it equal to 0. In this equation, I am just using the Laplacian operator del square instead of dou square by dou x square plus dou square by dou y square. Then, if we integrate this equation by parts, we get the following equation known as the weak form. And there is a reason it is known as the weak form, and I would like you to explore that aspect. If you observe the weak form equation, we have this term in terms of d gamma, which is a boundary term and is related to our boundary conditions. This weak form is one of the significant steps in the FEM process, and I would say this is where FEM starts. You may have two questions at this point. Number one, how does FEM convert the boundary value problem into linear system of equations? And number two, how all these equations fit into our process of FEM. These will be answered in the next slide. Just to remind you, we started with a boundary value problem and we ended with a weak form statement. Let's move forward. We have discussed this process before. Let's try to see how the mathematics is associated with these steps. The weak form, as we saw, is defined for the entire domain. After we mesh, we define the weak form for each element and not for the whole domain. I represents the ith element. Let's see what goes on in the element-wise calculations. This is where the magic happens. Let's isolate one element and see what's going on. The element here is a continuous domain. Imagine it's a collection of infinite points, and our unknown u hat I is a field quantity or a function defined for this element. Finding a function is always a complicated task. Instead of having our unknown as a function, if we could have our unknown as an array of numbers, that would make our life much easier. That is, instead of u hat x comma y, we have u1 hat, u2 hat, u3 hat and u4 hat defined at the respective nodes of the element. A function to just 4 numbers. Remember that. This transformation is done by what we call as the piecewise interpolation and is given by the following equation. U hat equals n1 u1 plus n2 u2 plus n3 u3 plus n4 u4. I personally believe that this is the magic equation of FEM. n1, n2, n3, n4 are known as shape functions in FEM, and importantly, they are the known functions which depend on the shape of the element. So, by this equation, we are writing an unknown function u hat in terms of known functions, all your n1, n2, n3, n4, and unknown numbers u1 hat, u2 hat, etc. We can also interpret this equation as a continuous to discrete transformation in some sense. Here's where the interesting part comes. If you substitute this u hat equation into the weak form and do some manipulations, you magically end up with a linear system of equations for that element. That's how FEM converts a boundary value problem into linear system of equations. And remember, this is just for one element. You need to do the same for each and every element. Here, small k is called as the element stiffness matrix, and small f vector in solid mechanics is called as the element load or force vector. The solution is not yet complete. Now, you need to add together the contribution of all the elements. When you do that, you get a linear system of equations for the whole domain as shown here. Capital K represents the global stiffness matrix, and capital F represents the global force vector, and the number of equations will be equal to your number of nodes. By solving this equation, we get u hat values at all the nodes in the domain. Then we could use the interpolation equation to obtain the field representation of u hat for the entire domain. Lastly, a common choice for the weight function w is the shape function n. When we do that, it is known as the Galerkin finite element method. That concludes the whole process of how FEM works. Let me take a step back and highlight the important points. We start with the boundary value problem, then we write the weighted residual statement, then we obtain the weak form for each element. Later we use the interpolation equation to obtain the element level quantities, and then we do assembly and obtain the global level quantities. Let me explain the power of FEM with an example. One of the important certification requirements for a car is the crash testing analysis. It is done to make sure that the passenger is safe in the event of an accident. Let's assume this analysis requires 1000 data points, which means you need to crash 1000 cars. But we know it is very costly and time consuming. Alternatively, we could just crash 100 cars using physical testing, and we could crash the rest of the 900 cars in our FE simulations, which just requires a computer. In that way, the power of FEM lies in enabling a virtual testing platform that saves a ton of money and time. Lastly, if you are a beginner, I would strongly recommend the book by Professor Seshu. It's very concise and well written. I really enjoyed reading this book. So thank you and see you some other time. Bye bye.